Hey, Mike, you can hear and see us okay?
Good, bud.
Thank you, sir.
first thing tonight is that, remember the capstone project. What was it? Friday, is that the 26th? 5 p.m. Right. You're going to post it in Dropbox and D2L titled Capstone Project. Yeah, we haven't talked about all of them yet, but yeah. The other thing I want to mention here. Look, I won't let you forget about that right there on Thursday, because Thursday is our last class and we'll have covered everything you need then. So I won't let you forget. Is our final. Okay? Sometime this week I'm going to post some old finals in D2L. There's under content there's a module there that says old finals. I'll post 2 or 3 of them, right? So you can look and see, the kind of questions and the style of questions that get asked from the project. Get asked from the final. And the other thing is this: is that our final is Thursday, the 2nd, from 6 to 8 p.m. So I'm going to circle that because that's a little different time than what we normally meet. I'm following the university final schedule, all right? And then the other thing is we're all moving. And what I mean is, you folks that are in section 521 in Brown Hall 132 with Rob now. So 521, you're going to be going to Gilbert, .106. Okay? You folks that are here with me, so you are section 531, you're going upstairs to room 336. And you folks that are streaming, okay, I know some of you always tell me you're going to Johnson City. You will be going to Gilbreth 106. And you folks that come to Kingsport, you will be going to room 336. So, the reason for all the moving around is the math department needs, it's kind of weird, we're in a stats class, and the math department needs data on this final. And so the easiest way for us to get the data is when you are done with your test, right? You're going to have your test. The test is going to have 43 questions on it. You're going to have the answer sheet that's got 43 numbers on there, just like we do for our normal test, right? The easiest way for us to get the data off the test is when you're done, you log into D2L, and you enter your answers. I didn't get everything sent to me in time to show you what it's going to look like. So in other words, here's the deal. There's 4 tests in the room when we take the test, right? There's a form A, B, C, or D. You'll go log into your D2L site, all right? And it'll be under assessments. In other words, what is it? Evaluations. I don't have it up. It's under evaluations, assessments. You'll pick your form. There's nothing there except number 1 says, my answer to this question is, and you'll pick A through E, right? There's 2 good reasons for this. 1, we get the data, and 2, after you put your answers in and you click submit, they're going to tell you your grade right then. You don't have to wait for nothing, all right? I will show you that at the beginning of class on Thursday, where it's going to be, they're password protected. That's the reason we're all moving, because every one of these rooms here has computers. It's not to do the test, it's to put your answers in so that we can get the data back in the end, all right? You folks that use proctors all the time, you will not be able to do this, so we won't get your data. That's okay. Your proctor will send back your answer sheet. I'll grade it by hand, and then I will post your grade in D2L so that you can see it, as soon as I get a chance to do that. Everybody understand we're moving, right? And what you need to bring with you is, I'm just going to say we need some version of an ID. Whether somebody asks you for it or not, some version of an ID. I'm supposed to say this, but I'll pick whatever. Okay? You're going to need a calculator, as always. And you always have those 6 pages of formulas and tables, right? Well, if you're taking it in Gilbert or here, I got the tables for you. I'll give that to you. All right? If you're going and using the Proctor, I'll try to remind you, please take your tables with you because I'm not going to send that and make your Proctor print those out. All right? So that's where we're at. I'll tell you the same story on Thursday, except I'll go to D2L and show you what one of the putting your answers in forms look like. All right? Actually, I just got the test this afternoon, and I haven't had a chance to look at it. And I'll be honest with you, I never looked at it. Now, I didn't forget this guy here. I would like to finish the chapter we're talking about, and I'll come back and we'll talk about this, all right? Because this problem here is out of the chapter about inference for a population mean where you don't know sigma. All right? So I'll come back to that. Where I left off on Thursday is I was talking to you about matched pairs. And the last thing I wrote up is, look, there's something called matched pairs T procedures where you look at the difference between the 2 treatments that we know there's only 2 treatments in a matched pairs, and then we do the 1 sample procedures, which is what I did for you last Thursday, on the differences. So what I thought we should do is we should find ourselves a problem. I don't want to do the example that's in the book. I went over here to page 474. Remember, I'm looking for something that's matched pairs. And I'd like to look at 20.38. Right, I wanted to make sure I had something that was matched pairs. Okay? And here's what it says. Kicking a helium-filled football. Does the football filled with helium travel farther than one with ordinary air? To test this, the Columbia Compass Dispatch conducted a study. 2 identical footballs, one filled with helium and one filled with air, ordinary air, were used. A casual observer was unable to detect the difference in the 2 footballs. A novice kicker was used to punt the footballs. A trial consisted of kicking both footballs in random order. In other words, you flip the coin, right? If he landed heads, he kicked the helium first. If he landed heads or tails, he kicked the air one fell first. Right? Every trial, every time he did this, the novice kicker, I'm saying he, every time the novice kicker kicked it, they flipped the coin to see which one went first. All right? And it says, the kicker did not know which football, the helium field or the air football he was kicking. Fine. Okay? The distance of each punt was recorded. Then another trial was conducted. We flipped the coin to see which one went first. A total of 39 trials were run. I'm sorry, I'm in such a habit of writing down how many was in my sample or how many trials I did. It is 39. All right? It says, here are the data for the 39 trials in yards that a football traveled. The difference, now, anytime you see matched pairs, and this is definitely matched pairs where we're treating the individual as the pair, right, and repeated trials for that one individual, how did they do the subtraction to get these differences? It's going to make a difference when I set up whatever I'm going to do here. So it tells me the differences are the helium minus air. So the mu here you're looking at, the mean difference, mu, is the mean difference. Of helium minus the air. Notice the order of the word. Right? So that's what we want to talk about, is this mean difference, right, between helium minus the air. And you'll notice the data here is nothing more than, there's 3 little things here for each one of the trials. There's 39 trials, right? Your sample size is 39 if you like. Each trial you've got how far the helium ball carried, how far the air ball carried, and then what was the difference between. Where you notice they're taking the helium minus the air. All right? It says, examine the data. Is it reasonable to use the T procedures? Now look, we got to have a little talk about this. The only thing that we can do, because you notice there's nowhere that I read that things were normal, those differences were normal, anything like that. All we can do is look at the data and see what we see. And how are we going to look at it? I'm going to find this data. This is chapter 20. The problem is 2038. Now you notice how this data looks, right? There's the trial 1 through 39, air, helium differences. The only thing we can do is to make ourselves like a stem plot or a histogram. I'm going to make a stem plot here to see what we see. Right? So this is how things really work. It's just like this. If you really don't know about the population distribution, look, shit, if you don't know its mean, mu, and you don't know the standard deviation, sigma, then you're not going to know what it looks like. So what you do is you take the data, and you make, it's going to be quantitative, right, these differences. You're going to make a stem plot or a histogram. I made a stem plot. And what am I looking for? I'm looking to see, do I see any outliers in the data? And what's my shape? Well, you know, every time I got to look at a stem and leaf, I got to do this to you, right? It looks fairly symmetric, doesn't it? I would be concerned if things were like badly skewed one way or the other, because that might tell me, hell, you know, the population distribution of the differences for every time those two balls would be kicked might be skewed, right? This is how, what we're doing is we're looking at the data, the shape of the data here to see, well, 39, that's a pretty large sample. Hell, I would expect the population distribution to probably look something like this, right? So it looks somewhat symmetric. I don't see anything bad. I don't see any bad skewness. So when I look at the question, examine the data. Is it reasonable to use the T procedures? Yeah, think about it. I was supposed to have some kind of simple random sample. Well, hell, I got a matched pairs experiment, which is just as good. And remember, the population distribution was supposed to be symmetric, single peak, and all that kind of shit. It didn't have to be normal. The only way we're going to ever talk about what the population distribution looks like, because we don't know. I don't know its mu, I don't know its sigma, and I sure as shit don't know what it really looks like. You look at the data. Yeah, I love reference. Man, we're going about our business. All right? Is everybody okay with that? That's how it really works, right? You know, all the other problems you've ever talked about, they tell me, oh yeah, you know, the population distribution is normal. You ain't gonna know that, right? This is how you do it. You look at the data and say, oh yeah, that's all right. Okay? It says, if your conclusion to part A is yes, and I'm going to be honest with you, I don't give a shit what your conclusion to part A is. We're going to do part B. Okay? Do the data give convincing evidence? I'm going back here because I'm looking at part B because I said things look pretty good. They're roughly symmetric. And I see that word again. What does that mean for me and you? I'm trying to get that shit stuck in your head. I'm not estimating anything. I'm giving you a test of significance because we want to know we have good evidence of something. I don't know what it is yet, but the good evidence is giving convincing evidence that the helium-filled football traveled further than the air-filled football. So let me ask you this. You see that little mu right there? If the helium travels further than the air, what would we expect about mu? See, because I'm going to do this to you. You know, anytime I write this, there's 4 pieces that have to be done. Right, because remember, the mu is the mean difference. Well, if the helium ball travels further, we would expect mu to be greater than 0. And whatever value shows up in the alternative always shows up in the null as equal, right? In other words, there was no difference between the helium field and the air field, right? They travel about the same. Now, I'm going to give you, obviously, we're not going to do all these degrees of freedom, read some table, and calculate some t-score. What I'm going to do is I'm going to go over here, and I want to go to stat, basic statistics, and remember, I'm supposed to do the one sample t procedures on the differences, right? What I've got is this. I don't really care about the summarized data. I showed you that last Thursday. And I don't even have the summarized data. I have the raw data, right? And what do I have? I have looking at the differences. In other words, I'm treating those differences like a variable I would have treated last Thursday. And then I want to perform a test of a hypothesis test. Remember, in Minitab, that's exactly what the value is in the null. And I want to click OK. And then I want to go back because I shouldn't have clicked OK. Because what's the second thing I'm always supposed to check? What kind of test do you have? Do I have a one-sided test to the low, one-sided to the high, not equal to? You notice it's always set to not equal to, so I'm not even going to look at my answer because I know it's wrong. What way am I supposed to be going? Do I want mu less than the hypothesized mean of 0? Do I want mu greater? I want that, right? Remember? Go back and look. Mu is greater than 0. I click OK. I click OK. And then when I scroll here a little bit, notice there's my guy. One-sided. They're actually writing out the null and the alternative the same way I did. And they're giving me my t-score. So back here, for this, that's number 1. Number 2 is my t-score, my t-statistic, my one sample t-statistic. My t-score is 0.42. Is that large or small? When the x bar you got of the differences is 0.42, standard error is greater than the mean. Is that a long way out the tails? What I want to know is, and this right here I would tell you is, you agree? I mean, because I know every time I pick a freaking problem, the z-score, the t-score is like 2.72 or -3, something like that. Here you've got a small one. And then so 3 is always your p-value. And do not freak out next Thursday if I just write p for the p-value. I always do this so you know exactly what I'm doing here. And so I come back and I say, can you read the p-value? Well, yeah, it's right there. The p-value is 0.339, right? Everybody see that, right? T-score, t-value, t-statistic, your test statistic, your p-value is 0.339. Folks, that's huge for a p-value. Remember, all p-values are between 0 and 1. You've got something that will happen 34% of the time if the null hypothesis is true. You understand that, right? That statement I just gave you the definition of the p-value value, right? I've got an outcome here. The mean of those differences, those 39 differences, is I would get something as extreme or more extreme than that 34% of the time if you're really centered at 0. In other words, if there's really no difference between them, folks, that's huge. Well, let me ask you this. Let's say I threw a significance level in here of 0.05. What do you think? Is your p-value bigger than 0.05? Hell, your p-value is bigger than the 10% level, the 20% level, the 25% level, the 30% level. You didn't find shit here. That's huge. All right? So what's step 4? Step 4 is always my conclusion. Well, then let me put it to you like this. You got one or two answers always here. Forget what the problem is. You always got one or two answers. Either we reject H0 in favor of the alternative, or we fail to reject H0. Which one of these is this? This is the one where it might be the first problem I did all semester. That's one thing I can say. The data are consistent with H0 being true. In the context of the problem, we didn't find evidence that helium makes the ball travel further on the average. That's what you were looking for, and you did not find it. You have a small t-score, a small test statistic, you had a large p-value. The data are consistent with ACE not being true. The data, we fail to reject H naught. You were looking for evidence that the helium made the ball travel further, and you did not find it. Now, I got to come back here and do something, all right? I don't want to find us another problem and calculate a confidence interval, so I want to show you how to calculate the confidence interval here. Okay? For this one, I can go to stat, basic statistics, one sample t. Remember, anytime you do a confidence interval with Minitab, it's always got to be a two-sided. If not, it won't give you both directions. So to get the confidence interval that we're used to seeing, I need to make sure that the alternative is always two-sided, so I go both ways. If I click OK, right there's my confidence interval. Everybody see it? 95% confidence interval for mu, the mean difference, is between minus 1.76 and 2.69. So I'm going to come over here, and I'm going to write this. My 95%, C equals 95% confidence interval for mu is the following. I got to go back and look. It was minus 1.76 out to 2.69. Okay? Everybody okay with that? So we got the software to calculate me the confidence interval. So what do we say? With 95% confidence, the true mean difference is between negative 1.76 and 2.69. I'm going to underline three things to you in this statement again. You gave everybody your success rate, you told me what you were trying to estimate, and you gave them the interval that they're supposed to be. All right? Now, I want to come back and look at Minitab again. All right? Now, you'll notice there's my N, there's your X bar, there's your S, there's your... Right, those are the same three pieces I was showing you, the same four pieces I was showing you last week, right? X bar, that's the mean of the differences. S, that's the standard deviation. S over the squared n, that's that standard error of X bar, right? That's our guidance. I wanted to do this even though the problem didn't ask, because okay, can you pick it out? Can you read it? Now, there's one more thing about Minitab we need to have a chat about. And, I know you're doing learning curve things, right? And you're not doing any of that shit by hand in this chapter. Surely you're not. Okay? My thought is this. Let's say there's problems that didn't give me the differences. Instead of me sitting there and doing this subtraction and keeping track of it, can I do just with helium and air? Okay. Stat, basic statistics. Now, if you'll notice, the seventh one down says paired heat. Each sample is in its own column. I'm going to take sample 1 and I'm going to put helium in there. I'm going to take sample 2 and I'm going to put air in there. Right? In other words, what Minitab will do for me, if the differences aren't already sitting there looking for me, it will do the difference. All right? And I'm going to choose options. And notice the hypothesized mean here is supposed to be 0. I want greater than, same as I did before. Notice that's all on the same page here. If I click OK, and I click OK, I get the exact same answer. That's the reason I scroll to the bottom here, right? My hypotheses are exactly the same. The t-score is still 0.42, and your p-value is 0.339. I did this as a matched pairs t procedure using Minitab, because if I'm using a book, I'm supposed to find the differences. It did it without me finding the differences. Everybody follow here. So I know there's problems in Learning Curve where they don't give you the differences. They just give you the values of each one, and you have to be able to do it. And I don't want to sit there, especially if I got hell, I don't want to do it with 10 of them. If I've got 100 of them, do I want to sit there and do the subtraction all the way through? Hell no. I just showed you how to do it. Now notice, use the mean difference. And the thing about this is, I got a circle. And I know, I kind of thought you guys would be enjoying Minitab at this point because I've stopped calculating. I'm interpreting now, right? Reading and interpreting. You see that part I've got circled? Notice I do have the mu being right? It's the helium minus the air. You notice I put helium as sample 1, air as sample 2. Minitab always takes sample 1 minus sample 2. Everybody follow that, okay? Okay. I wanted to show you both ways. Now, the last thing for me and you to talk about here in this chapter is something called the robustness of T procedures. Translation is, how much can I tolerate, or how much can I get away with and still trust my confidence interval and still trust the p-value of the test? In other words, how much can I violate where, I'm not supposed to have any outliers, I'm not supposed to have any skewness? How much can I get away with and still trust the confidence interval and your p-value? Well, this depends on the sample size Now, I'm going to refer you to a box here, all right? There's a box in your, and it's on page 466. Now, one thing I would definitely do before I went and took the test Thursday, I would make sure I know all my little conditions. This is a condition here. Remember, I'm supposed to have a simple random sample. The population distribution is supposed to be symmetric and single peak. We always look at the data to see if it's symmetric and single peak. On this page here it says, I'm going to read this little box to you. The box says, using T procedures. When can we trust the confidence interval? When can we trust our p-value? And it says this, except in the case of small samples is less than 40, okay? The condition that the data are an SRS for the population of interest is more important than the condition that the population distribution is normal. So when your sample size is less than 40, we have to pay attention. Bigger than 40, the more important thing is that you're looking at a simple random sample, okay? And so it says this, it breaks it into three pieces. If your sample size is less than 15, very small sample in the big scheme of things, use T procedures if the data appear close to normal, roughly symmetric, single peak and no outliers. If the data are clearly skewed or if the outliers are present, do not use T. Well, you can use it, you just can't trust them. So from 15 down, you can't get away with anything. You can't get away with any outliers, and you can't get away with any skewness. Sample size from 15 to 40. I know, it says at least 15. I'm going from 15 to 40. The T procedures can be used except in the presence of outliers or strong skewness. In other words, you can get away with, between 15 and 40, you can get away with a little bit of skewness. And then the last one is, if you are bigger than 40, the T procedures can be used for clearly skewed distributions when the sample size is large, bigger than or equal to 40. In other words, when it's bigger than or equal to 40, the most important thing is that you're looking at a simple random sample. Between 2 and 15, you can't get away with anything. Between 15 and 40, you can get away with a little bit of skewness, still no outliers. Bigger than 40, you better have a simple random sample. That's the deal. All right? Now, I'd like to go look at this guy here, if you don't mind. Problem 6 on the capstone. This is a one sample key problem. All right? It says, in 2018, Gallup conducted a survey of retirement. One question was asked was the same as question 13 on the survey. Question 13 asked, at what age do you expect to retire? Gallup asked this question for 3 different age groups. It was found that the average age one expects to retire for age group 18 to 29 was 63. Since the majority of students taking Math 1530 fall in the 18 to 29 age group, the variable retire, age 18 to 19, was created. This variable contains the values of what age a student expects to retire for those that were said that they were 18 to 29. On average, is the age of that ETSU students, age 18 to 29, expect to retire different from the age reported in the survey of 63. Okay? Create a suitable graph to display the distribution of retired age 18 to 29 reported by our sample. Well, you got 2 choices. You can either make a stem plot or you can make a histogram. Right? That's your 2 choices. I'm going to make a histogram, and why? Because you got to remember, my sample size here is like 600. The stem plot's going to look really bad. I'm going to make a histogram, and I want a simple one, and I want to go over here, and I want to... I want a histogram, simple one, and I want what? Retire. Make sure you use the retired age 18 to 29 here. And I'm going to click OK. So notice, this looks like roughly symmetric here, doesn't it? And there might be a little bit of skewness. There might be a possible outlier or 2. Okay? But that would be the graph I would take. That would be the graph I'd put over there. Then it says, using alpha equal 0.05, the 5% significance level, perform a test of significance to see on average, if on average the age that ETSU students 18 to 29 expect to retire is different, and I'm going to read that word one more time, different from what was reported in the survey of 63. Anybody know what the null hypothesis is? If you don't want to start there, does anybody know what the alternative is? It's a story about mu, right? The mean age that these people would say they're going to retire, age 18 to 29. You understand? The alternative is mu does not equal what's in the survey. The alternative is, the null is mu is equal to whatever is in the survey. This is a 2-sided problem here, yes? It says different from what was in the survey. The null should be mu is equal to some value. The alternative should be mu does not equal some value. It says using Minitab to perform the appropriate test, copy and paste the output here. Okay. Now this was just like one we did last week. Stat, basic statistics, 1 sample T. I want my samples in a single column, and I want to do retired age 18 to 29. The value that's going to show up in the null, does anybody know what it is? Would somebody just say it out loud so you could say you told me and I didn't tell you everything that was on the project? Is it 63? Okay. 63. Okay. Let's make sure we've got a 2-sided test. Do options. 2-sided test. Okay. Okay. There's your test. If null, the alternative, that's what you got to type in the Word document here. It says, what is the name of your test statistic and what is its value? I'm pretty sure it's a t-test statistic, right? Because it's a t-score. And what was its value? Its value was minus 2.27. Let me ask you that. Is minus 2.27 large or small? I don't care about the minus sign. I know the minus sign means to the left. Is 2.27, is that large or small? That is large. We're expecting a small p-value. We have it. The p-value is 0.024. Yes? I come back here. It says, what's the p-value of your test? Well, you're just reading it off the printout. I just told you what it was. It was 0.024. State your decision regarding the hypothesis being tested. What I want to know is, do you want to reject H naught in favor of the alternative? Or should we fail to reject H naught? Which one of these is this one? You have a large test statistic, you have a large t-score, and a small p-value. What do? Well, if you don't remember, folks, this one here is just the opposite. You had a small test statistic, a large p-value, and we prefer to reject H naught. Over here, you have a large test statistic, t-score, t-test statistic, one sample t-test statistic, all the words, and a small p-value. That's when you want to reject H naught in favor of your alternative, right? Then it says, state your conclusions, use complete sentences. In other words, in terms of the context of the problem. We have significant evidence at the alpha equals 0.05 level. We have significant evidence at the 5% level that the mean retirement age for people for the age group 18 to 29 is different than 63 that was reported in the survey on the average. We want to reject the null in favor of the alternative. At the 5% level, we have significant evidence that the mean retirement age for the age group 18 to 29 is different from 63, that which was reported in the survey on the average. Part H, what assumptions are you making to carry out this test? What's the first assumption? What's the first condition every time me and you talk about anything? We're assuming that the ETSU students that took the survey were age 18 to 29 can be considered a simple random sample from the age group of 18 to 29. That's the first thing you're assuming. And then, is the p-value valid in this case? In other words, can we trust what we just did? In other words, what am I asking you about? What are they asking you about? They're asking you about that. What's your sample size? You bigger than 40? That's all I want to know. Are you bigger than the 40 I need? Your sample size here, remember, it's not everybody that took the class survey, it's only the ones 18 to 29. Your sample size here is 559. Do I need to worry about the outliers? Do I need to worry about, I said something looked like slightly skewed. Do I need to worry about that? You guys are all looking at your computers, and I'm telling you the answer here is I don't need to worry shit about that. Right? My sample size is way bigger than 40. I don't have to worry about any skewness. What did I need to worry about? Because my sample size is 559, I need to worry about that I had a simple, random sample is what I needed to worry about. What was the assumption I was making? The assumption I was making was that we have a simple random sample. Okay? Now, has anybody went back and looked at any of the old capstone projects I posted the solutions? I'd go back and look at them. Just to get all the wording I gave you here today, right? It's the same style. Obviously, the variable changes. I can't remember if the last ones have been two-sided or one-sided tests, but the language is still the same. Remember, you've got a large test statistic, you've got a large t-score, you've got a small p-value. I want to reject the null in favor of the alternative. And then part G, state your conclusion, use complete sentences in the context of the problem. Okay? Can I come over here and just look at one more thing? I'm just curious about something here in Minitab and this problem. Suppose I didn't pick a stem plot or a histogram. Suppose I picked the box plot. Isn't that another way to show quantitative variable? The reason I'm cheating here is I want to see if I got outliers. I got outliers? I got a lot of them. Right? Should I be concerned? Actually, at this point, I don't even want to count how many I got. you might want to put a little note there at the bottom of that one that, yeah, I understand my sample size is 559 and I should be fine. But when I looked at the stem plot, with the box plot, oh, there's a whole shit about that. And the weird thing is they're on both sides. Might want to make a note of that. It's just a thought. Okay? Now, are we okay? We're all caught up as far as the material goes with our project, right? What's the only thing that's left? It's number 5. There's a bonus there for a two-way table. In Word? Okay. I'm looking for. Oh no! See, my problem is at the house. I could have showed you like but it's on a map. Where's it at? Where's the? Oh yeah. I might have to search here, but there it is. Symbol. Okay. Your X bars there because you're trying to type in the hypothesis. Yes. Yeah. There it is. Now, we got to go to the next chapter we're going to cover. I know some of your other classes has thought that like the semester was over last week. It's not. Okay, that's just not my style. And so I would like to go to chapter 21. And chapter 21 is comparing two means. Now, me and you've not done any of this where there's been two of anything. You know, it's always been a mu or a p we talked about when we were talking about proportions. Now, there is going to be two of everything. There's going to be two populations, two population means, two population standard deviations, two sample sizes, two samples, two X bars, two S's, two of everything. All right? So what I would like to do is I want to think about there's two populations or even, two treatments. And I would like to compare either the two population means or the two treatments on two different groups. All right? Now, I'm going to be a little picky here. And my first thought is the goal of inference here, where you're looking at comparing two means. Is to compare responses to two treatments. There's an or compare means of two populations. Okay? Now, first time ever here, I need separate samples. No matching. Matching is not a two-sample problem. It's not two of anything. No matching, and your samples can be different sizes. I mean, you can have one sample of size 40 and the other sample of size 55, and everything is going to go well for you. All right? Now, how does all this work? I'm interested in comparing, one more time, two population means. mu1, and mu2. The starting point is make stem plot / histogram, whichever is your favorite, and you want to compare. Now, obviously, this is of the data, right, of each sample, and you want to compare shapes, centers, spreads of the two samples. The conditions that need to be met in this chapter, anybody know number one? Oh, normally it's just an SRS, right? But there's two populations of samples. I need two SRS. Okay? From distinct populations. In other words, there's this population here, there's this population here. I need a simple random sample from this population, I need a simple random sample from this population. Two distinct populations, two distinct samples. In my samples, I'm going to go back and pick out a word from our probability. Are independent. In other words, knowing who is in or what is in this sample tells me nothing about this sample. It's like the two samples, like I said, the two samples are separate. This is population, this population. Nothing in here tells me anything about here. Nothing in here tells me anything about here. They're two separate samples, two independent samples. Two, both population distributions need to be this. You know, I'm supposed to write they should be normal here, but you know that that's not true. What's true is they need to have similar shapes. No strong outliers. 3, this is where I told you I don't know the mean and standard deviation of the population. What I'm going to tell you is I don't know the means and standard deviations are unknown. All right? So here's the deal. I'm going to write and make you like a little table here, what's going on, because there's so much going on at this point. What's going on is I'm going to have a population, and I know they're distinct and separate. So there's a population 1, there's a population 2. The variable that we are interested, we're going to measure the same variable in both populations of both samples. I need to subscript it. I just can't use an x now. There's got to be an x1 and x2. It's the same variable, but x1 is for population 1, x2 is for population 2. The mean of your population, you know we always use mu, but I got a subscript. And the standard deviation, we always use sigma, but I got a subscript. There's two populations. There's two population means, and there's two population standard deviations. Okay? We're going to choose a sample size, right? We've got to take a sample. We're going to take an SRS from population 1, an SRS from population 2. We have to use n. We're going to subscript with 1 and 2, so that's the sample size of population 1. That's the sample size out of population 2. The sample mean. We're using X bar. I'm subscripting to let you know which sample it came from. The sample standard deviation. You know, sample standard deviation, we always use S. There's one for each sample here. Like I warned you, there's two of everything. Two populations, two population means, two population standard deviations, two sample size, two sample means, two sample standard deviations. And I'm going to do the obvious thing. And the obvious thing is, we always want to use our statistics, and maybe I should have said that here. You see these four here? Those are parameters. Those are unknown quantities about your population. You see these guys here? These are your statistics. Oh, there's a pile of shit going on here. Okay? And so, we always want to use our statistics to estimate the appropriate parameters. So I want to use the sample mean from sample 1, and I write x bar 1, subscript with a 1, to estimate the mean from population 1, because that's where that sample mean came from, was the sample from population 1. I would like to use the sample mean from the second sample to estimate the mean of population 2, because that's where that sample came from. I would like to use the standard deviation from the first sample to estimate the standard deviation of population 1. I'd like to use the standard deviation from sample 2 to estimate. I'm doing what I'm thinking is the logical thing here, right? I'm using the appropriate statistics to estimate my unknown parameters. The problem is there's two of everything here, right? There's two means, there's two samples, up here and down here. So we're doing the appropriate thing here. The punchline is to do inference. About now, I made a big deal about this Thursday. I made a big deal about this when I did the matched pairs. Remember the matched pairs? What was the language I was using? It was mean difference, right? You see what that is? What would be the language here? My statistician's trying to get crazy with me when I get real picky about the language. The language tells you what you're looking at. Oh, if you're talking about mean difference, hell, I know you're talking about matched pairs. If you're talking about the difference of the means, hell, I know there's two populations, two means. That's what you're talking about, right? We start with, in other words, how would you estimate that? I'm going back here. I'm going to use x bar sub 1 to estimate mu1, x bar sub 2 to estimate mu2. How would I estimate mu1 minus mu2? I would start with the difference of the sample means. Right? That's the way you do it. You're going to estimate each piece like that. Now, I'm going to do this. I want you to realize this is about the population. And down here is about your samples, right? That's where that comes from. In other words, those are your parameters. The difference of those two parameters, you want to estimate that with the difference of your two statistics down here at the bottom. Okay? Now, I'm going to get right to the point here. There are two samples. This is what this chapter is all about, is these two sample problems. And I'm thinking about two sample T procedures. One more thing, they're not one sample problems, they're not matched pairs. These are distinct problems by themselves. Two samples, two populations, right? That's what you have here. I got to look at all of these for a second. Everybody's got the right look to them. You know, because the last Tuesday we'll be together. I got like things I'm dealing with here all at one time, right? I don't want to really write down and say, I want to standardize this or I want to standardize that, and, I'm going to have a standard error because I want to follow what I was doing. I would like to get to the point here and say this. The two sample key statistic. We've talked about the one sample t statistic. Now that's what was on the project there. Would look like this. The difference of the sample means, and what would I divide by? I got to circle this. This right here is called the standard error. I'm still playing in that standard error game that I've played since the proportion. Right, that's the standard error. That would be my t-score this time, this t-statistic. Just for the sake of things, this measures how far the difference of the two sample means, x1 bar, x sub 1 bar, x sub 2 bar, is from 0 in standard error units. Same as I did with you with the t-score, right? The t-score back there measured how many standard errors away your x bar was. Well, here it's measuring how many standard errors away x1, x bar sub 1 minus x bar sub 2 is from 0. Now, here's where we're at in the semester. Yeah, we're on our 27th night. The deal is t does not have a t distribution. So I've been putting all kinds of bad stuff on you guys this last week or so. Last week when we did the t stuff, that thing wasn't no longer normal, right? We had a t distribution. Now what the hell we're looking at, well, it's not normal. It don't even have a t distribution. But the deal is this, all right? In practice, in the real world, when people work these kind of problems, a t distribution is t-distribution approximation. In other words, approximating what you're using, what you're looking at, is very accurate. So that's a fancy way of saying, yeah, okay, that t statistic up there, it doesn't have a t distribution, but we're going to approximate what we're seeing with the t distribution. It's very accurate. So there's two options for which t distribution. And I'm going to put in blue here. Remember, we always pick out our t distribution by telling me the degrees of freedom. Before it was 1 minus your sample size, right, in the previous chapter. Well, here, I'm going to give you a number 1. We can let the software pick which t distribution, what degrees of freedom you want, or use the degrees of freedom equal to the first sample size minus 1, or the degrees of freedom equal to the second sample size minus 1, the smaller of those two. We can do that. But what we're going to do is we'll let the software pick. because many tables split up and say, oh, okay, this is the t distribution I use, this is what the degrees for free. Now, here's the thing. I'm not going to write out some estimate plus or minus a margin of error for your confidence interval. There is, right? There's a confidence interval. There's a confidence interval. Level C, confidence interval for the difference of the means. Okay? And there is a test of significance. Now, in a test of significance where you're trying to compare two population means, the null is always the same. I know, that's the first time I've written any kind of hypothesis and there wasn't a value in there. When you're doing two sample problems, the null hypothesis is the two population means are equal. Anybody got an idea or a thought about what my alternatives can be? There's three possibilities. See these? One side. Two sides. Still no value. See, the one about mu1 does not equal mu2, we would want to know, oh, is there a difference in the two population means? The one on the top there was the population mean of population 1 greater than the population mean of population 2. The middle one there is just the opposite. That's your only options when you are doing a test of significance and you're talking about comparing two population means. Null is always they're equal, and the alternative is either greater than, less than, or not equal to, the same as we always have our three alternatives. All right? Now, before I do a problem here, because that's where I'm at, you notice I did good. I didn't write any bad formulas down. The worst one I wrote down for you here was that. Okay, here's what my key statistic would look like. I didn't show you any tables and trying to read any t-scores or anything like that off of there. We should be able to state the hypothesis, and I would like to keep this thought in your mind. The difference of the population means, not the mean difference. Mean difference means matched pairs. Difference of the population mean means two sample problems. I would like to do one other thing here, and then I'm going to pick out a problem and we're going to work through it. All right? You know, out of all the chapters mean you've done, this is probably the shortest one mean you're going to do. Why? Because I'm not calculating anything by hand. And that's about as simple. To be honest with you, that seems right here to be way simpler than all the other tests of significance I try to write anything down. Okay? My thought is this. Robustness again. That's where I'm at. Okay? In other words, now that I've got two populations, two samples, and all this, how much can I get away with? And so what we're going to do is we're going to go back to that page, and I'm going to remind you that page one more time. It was page 466. Go back to page 466 where we were looking at, I can use the term money now. In that chapter there, those were one sample problems. These are two sample problems. We talked about the sample size telling me something about what I can get away with, how robust my T procedures are. What you do is you replace sample size in, right? Because if you're between 2 and 15, you can't get away with anything. Between 15 and 40, you can get away with a little bit of skewness, still not higher. Bigger than 40, the most important thing was that you had a simple random sample. So you go back and you replace n by the sum So what I'm worried about is the sum of the two sample sizes are between 2 and 15. I can't get away with anything in my sample, just my sample. If I'm between 15 and 40, I can get away with a little bit of skewness in my two samples. I can't get away with any outliers. If the sum of the two sample sizes are bigger than 40, the most important thing to me is that I've got two simple random samples from my two distinct populations. That's the deal. So you go back and you replace n on page 466 with add the two sample sizes together here in chapter 21. All right? Now, I'd like to find us a problem we can do, and I'm definitely not going to do anything by hand here. The one I was thinking about is, I don't want to do the ones that are examples here. I'd like to go to page 491 if you don't mind. And I'd like to look at problem 21.9. There's a lot going on there, and there's enough for us to see what's happening here. What I've got is this. It says, do good smells bring good business? I don't know. Businesses know that customers often respond to background music. Do they also respond to odors that are in wherever? It says, one study of this question took place at a small pizza restaurant in France on 2 Saturday evenings in May. On one of these evenings, a relaxing lavender odor was spread through the restaurant. On the other evening, no scent was used. Table 21.2, which is on page 492, gives the time in minutes that the two samples of 30 customers spent in the restaurant and the amount that they spent. So there's actually two things. You've got the lavender odor, we've got this sample of 30, how long did they spend, how much did they, the time that they spent and how much money they spent. And then you've got this other sample size 30 where there's no odor special in the restaurant, how much money they spent, and the time they spent in the restaurant. And it says this, the two evenings were comparable in many ways, weather, customer count, and so on. So we're willing to regard the data as independent SRSs. Of course they are. That's condition number 1, right? So you're thinking about this as being a simple random sample when the lavender odor is there. You're thinking about this as being a simple random sample when there was no special odor there. Okay? It says, the authors say, therefore at this stage it would be impossible to generalize the results to other restaurants, but at least we can say something at that restaurant because your sample's coming out of that restaurant. You understand? You can't go any bigger than where you're looking at your population, right? Okay, so part A says this. Does a lavender odor encourage customers to stay longer in the restaurant? Examine the time data and explain why they are suitable for two sample T procedures. Use the two sample T test to answer the question posed. So I'm going to do this. I'm not going to use population 1 and population 2. I'm going to use the mean mu subscript without. And this is the mean time spent with the lavender odor. I'm going to use N for no odor. This is the mean time spent with no odor. Right? If I can do it like that, where I can somehow keep track of what I'm seeing, okay, that's the mean time spent with the lavender odor, this is the mean time spent with no odor, I would do that. You understand, it says, does the lavender odor encourage customers to stay? Use the two sample T test. We want to test the significance, right? So, I already told you, every time I'm doing a two sample problem, they're equal. And then whatever notation you use for the two population means, I left you in blank here. You got three options: greater than, less than, or not equal to. I'm going to go back and look again. It says, does a lavender odor encourage customers to stay longer? That means mu sub L should be, agreed? Okay, right? So we stated our hypothesis. And then question. What was my sample size? Agreed? Both nights they had samples of size 30, right? Does everybody understand why I added them up? Because I'm worried about this right here. I'll come back. I'm worried about this part here. I'm supposed to add them, right? And when I added the two sample sizes, 30 plus 30, I got 60. So what's the most important thing to us? So you have two distinct separate SRSs, and it said, assume that we do, right? So we should be good. I'm going to show you how to check that in Minitab. And so we need to find this file. I need to go to chapter 21. I need to find 21, what was it, 9? So you notice that's nothing more than that table that's on page 492, right? That's all. I've got two of them, right? I got the minutes with no odor, I got the euros with no odor, minutes with lavender odor, euros with lavender odor. They measure two different things. I'm interested in the minutes spent, all right? And so I want to do a two-sample problem. If you look at the fifth one down, we've been all over this place, right? We've had the one sample T, we've had the pairs T, now we're looking at a two-sample problem, two distinct populations, two independent samples. So I want a two-sample T. Now, you've got options here. And the reason I click that is both samples are in one column. It's possible I have them both in one column. Or it's possible that I have them in separate columns, which is the way we have it. Or it's possible I have the summarized data. What's the summarized data? I have my X bars, I have my S's, and I have my N's. Remember, we can always do it if you have the summarized data. I showed you that last Thursday. Okay? What we have is each sample is in its own column. Right? Now, very important. What I tell you about matched pairs. We always take sample 1 to be this one and sample 2 to be that one. I'm going to put the minutes with the lavender odor sample 1, the minutes with no odor in sample 2. Everybody follow? Now, if I screw this up, we'll come back and flip these the other way. Because the reason we got to pay attention is, if it was a two-sided test, nobody would give a shit, right? Null is are both equal, the alternatives are different. We don't have a two-sided test. We got the mean of the lavender odor is greater, right? So we want to make sure we have the right direction. I'm going to do options. Now, you notice that hypothesized difference. Here's the thing with Minitab, right? It's this. I want to see how you follow. You see this part right here? All right? Minitab has a hard time me writing in that they're equal. What they do is this. Is this also just another way to write this? Is that the same? If they're equal, then their difference is 0, right? That's the way Minitab's taken it, that the mu of the lavender odor minus the mu of the no odor is equal to 0. What do I have down here? That's the only way it will go in Minitab. All right? So when I come over here, I got to tell it 0. If it'll let me write on this, I'm going to write on it. Everybody see that part right there? Sample 1 mean minus sample 2 mean. The mean of the lavender minus the mean of the no odor. It's just to get everything in the right place. All right? And then, what do I need? I need it to be bigger than the hypothesized difference. Right? I need it to be bigger than 0. Remember, Minitab is taking it the way I have it written in red. It's much easier for me to think about the way I wrote it originally. And I don't care about a confidence interval or anything. I don't care about assuming any. I'm not going to make any assumptions here. I'm going to click OK. I'm going to click OK. And so what this gives me is, it gives me all kinds of information. It gives me my sample sizes, my X bars, my S's, my standard error. There's 2 of everything, right? The estimate for my difference, I don't care about that. Notice how Minitab is writing your null and your alternative. The null is or equal. The alternative is that the use of 1 is greater than the use of 2. maybe what I should ask you is can everybody pick out the t-score here? What is it? My t here is 3.98. What's my p? You know it can't be exactly 0. What was the degrees of freedom it used? Minitab does some crazy stuff on the degrees of freedom. In other words, just using the t distribution with 57 degrees of freedom. I can show you the calculation, but it's that big. I mean, it wasn't like they took 29 or whatever, one less than the sample size. They did something way crazier than that. They got a better approximation than us using what I told you earlier. Now, what do you want to do? Oh, I know. I'm in a different chapter. I've given you the same steps. 4. What's the conclusion? You got a large test statistic. You got a small p-value. What do? Reject. H not. In favor. Of the alternative. What does that mean here? We got strong evidence that customers stay longer with the library. All I'm telling you is you've got strong evidence in favor of the alternative. The alternative was that they stayed longer on the average with, let me throw in on the average, than they did with no load. Can I show you one other thing in Minitab? I want to see how you react to this. Because, I know I got Minitab to do all the work for me, but there was one other thing I wanted to show you here. If I go back to where I was, 2 sample problem, right? Because there's 2 distinct populations and all that. If I went to graphs, right? I've not graphed anything for you on any of these. If I go to graphs and I would like to do box plot, and I click OK, and I click OK. Now all my other stuff is the same, but what it's done is it's given me a box plot for the minutes with the lavender odor, it gave me a box plot with the minutes with no odor. How things look. Well, the no odor looks like it's roughly symmetric. The lavender odor looks like it's a little bit skewed to the left because the median is closer to the third. The minutes with the lavender odor has a high outlier, right? Yeah? Do I need to worry about any of that shit? My sample size added together is 60. I'm bigger than 40. My most important thing was I had 2 simple random samples. Yes? One more thing. If it'll let me write. You see this? That is what that is. That's what it's showing. It's showing me the mean with the lavender odor time, the mean with the no odor. You see this? If they were about the same height, what would you expect? I would expect a small t-score and a large p-value. The further they do this, the bigger the difference, the larger the t-statistic, the smaller the p-value. See how they moved a little bit? In other words, I could have answered the question without doing the test just by looking at this, because I see this. There's got to be some point where here they're not significant, right? And as I start moving, they become significant, right? And here, shit, you got everything you wanted. So I definitely see that it looks like it does work out the way the test tells me, and it's based off of these side-by-side box plots. One last thing. I know it's time to go home. I want to finish this one up. And here's what I want to do. Let's say I wanted a confidence interval for this. Just like before, all that stays the same. But remember, you got to have it set as a 2-sided test every time you do this. If I click OK, of course, give me back my picture. But you notice it's got everything labeled for me. And then, can everybody pick this out? Yeah, I'm going to say stupid shit here. that your 95% confidence interval goes from 7.17 to 21.20, right? That's what we're reading. What does that mean? That means we are 95% confident that the difference of the means, the mean time spent with the lavender odor and the mean time spent with no odor, is between 7.17 and 21.7 minutes. I don't have time to write it down for you because I'm already out of time. Notice my language. We are 95% confident. Hell, that's not new. That the difference of the mean with time spent with the lavender odor and the mean time spent with the no odor, is in the interval, right? I want to get that language in your head. Mean difference, match pairs. Difference of means, through sample problem. On Thursday, we'll talk about the final chapter. I may come back and say some more about this, but I don't want to do any hand calculations here. I don't even want to write the formulas down for you. You still should be able to write down the hypothesis for a two-sample problem, right? And then get Minitab to print out whatever, all right? So make sure you get your homeworks back. Be careful going to the house. We will see you on Thursday.